All right, so we'll continue, and we are switching to something which I hope will, the topic today is obviously touching everybody, and I will be talking about our attempts to convert the hypothesis into something which can work in humans eventually, and specifically about our attempts to follow one of the most attractive to me hypotheses on specific causes of aging in mammals, and look at that as something which is druggable and potentially reversible. So I will continue arguing with Leonard, who actually said that aging is not a disease. I think that by making a psychological twist and push yourself thinking that it is a disease is a very important condition to make the problem approachable. Because as long as you think that this is a law of nature, you have no incentive to go there because you're ashamed of dealing with something which cannot be treatable. If it is a law of nature, it's equivalent to perpetuum mobile, and nobody is making perpetuum mobiles anymore. And however, unlike perpetuum mobile, nature provides you with examples of mammals which do not age. At least they do not show any frailty associated with their long life. And this animal named naked mole rat is one of the few representatives of that kind. It has the size of a mouse. It is documented to live at least 30 years without indications of acquisition of frailty. So to a certain degree, this make this paradox proven by nature, and if we one day would decide why this thing lives forever, 30 years is forever for a mouse, we probably could learn a lot more about why do we age. So my argument is that everything can be named a disease which you can treat. If there obviously aging is a pathology, it's enough to look at old people and compare them with themselves young. And if you can treat, delay, or do prophylaxis of this pathology, and you have the drug, there will be no choice for the FDA but to approve this drug and allow prescribing it and do reimbursement, right? From that moment, it becomes a disease. Sorry. So, well, among multiple theories of aging, one has always been closer to my heart from beginning of 90s, and this is the idea that our body is the place which accumulates gradually from every year lots of cells which do not exist at the moment of birth, named senescent cells. So these cells, which predominantly accumulate in connective tissue, mesenchymal origin, and what is happening is that when the cells undergo internal stresses such as sporadic, by mistake happening activation of oncogenic pathways, or breaking DNA during replication, or during recombination, or as a result of external stress, these cells can convert itself by epigenetic transition into the state named senescence, which can be defined as an epigenetic reprogramming of cells, like differentiation, as Arnie rightfully said today, which is associated with irreversible growth arrest and activation of certain properties which normally cells do not do, such as activation of the pathway which controls normally immune responses, like in F-kappa B, which leads to acquisition of so-called secretory phenotypes. So these cells start releasing bioactive factors, many of which are pro-inflammatory. It's to a certain degree, you may say the cells start to smell badly. And by smelling badly, it spoils the surrounding microenvironment. With time, the theory is that at the early stage of life, there are very few of them, and their impact on the general inflammation of tissues is very low. However, with time, their proportion is growing. And in the end, they create conditions in which the stroma and connective tissue forms the stroma of tissues is becoming poisonous. So it's a young stroma consisting of nice-looking fibroblasts which executes two roles. It forms a matrix for the tissue, and it also educates epithelium and other tissues whom to become. With age, this stroma accumulates senescent cells which secrete pro-inflammatory factors, change the microenvironment by becoming bad educators and also adding inflammation. So, and there is tons of evidence in literature showing that chronic inflammation is indeed the hallmark of aging, and it is very easy to make connection of multiple age-related diseases to how it stems from this inflammation, including cardiovascular, neurodegenerative, metabolic cancer, you name it. So the theory recently, 2 years ago or 3 years ago, received a very strong support by the paper published by Jim Kirkland and Jan van Dersen from Mayo Clinic, and who tested this hypothesis. The biggest proponent of this hypothesis is Judy Campisi, but they actually followed this theory and did the work. They made artificial mice, which is prematurely aged because of some genetic defects and accumulates lots of senescent cells. And they marked these cells by artificial protein which is expressed under senescence-specific promoter, making it possible to eliminate these cells from the body. And they indeed documented reversion of multiple traces of aging without increasing longevity. It's very important. Longevity and aging are indeed two different things. And this work created a big splash in the field, indicating that indeed by removing senescent cells systemically, you can rejuvenate the body and you can die young. So that's the idea. So, well, what is happening in naked mole rat? This is another piece of evidence. So if this is us, which actually have this process of senescence, which we interpret as the mechanism of cancer prevention, because it's a punishment of cells which happen to make a sin of allowing themselves to pass through the oncogenic stress or genotoxic stress, and therefore may create the pool of cells for, thank you, I hope it's wide. So, and you physicists, you know better. So, and this is equivalent of life in prison in human society for bad behavior. So, and well, what is happening in naked mole rat? This is us. We believe that in humans process goes the same way. In naked mole rat, as we showed in a collective work with Vera Gorbunova's lab in Rochester, New York, that they actually do not have senescence. If you plate their cells in culture, they die from the process which is apoptosis, interferon driven. They cannot not only see traces of aging in these animals, but they also cannot induce any cancer in them. So basically it looks like nature exercised here another principle of eliminating bad behaving cells. And instead of life in prison, they're getting death penalty, and it appeared to be much healthier for the society. Don't draw any political conclusions from my statement. So, well, what we decided, senescent cell accumulation not only really drive aging process, but you can actually manifest their presence in a very simple experiments, but you give quite shocking results. If you take the mouse and allow it to age naturally, and then you inject B16 melanoma cells in its vein and look how they grow as colonies in lungs, you mimic metastasis process. So, however, if you do the same, but you irradiate the mouse when it was young, wait for a long, do bone marrow transplantation to restore its immune system and blood, and in many, many months, you can do it a year later, which is equivalent to like half of human life, you are comparing their ability to maintain growth of melanoma, the difference you will see will be like this, 40 times difference. That's what basically happening with us after we go through chemotherapy and radiation. Our body forever remembers the situation and becomes prone to metastases. So there is a strong belief that it may be associated with senescent cells, as you will hear later in the talk. So, based on all this, we were inspired to formulate the following founding concept that aging results from systemic poisoning induced by pathological secretion of accumulated cells, and therefore selective eradication or blocking poisonous secretion by these cells can be the way not only to treat aging and age-related diseases, but also approach to overcome negative effects of cancer treatment on quality of life of cancer survivors, because they pass through this stress more severely than others. So the natural criticism we found was, and actually this particular criticism came from one of the former heads, directors of NCI, is that, oh guys, we already know how difficult it is to eradicate your own cells from the body, because that's what we are doing for cancer treatment. You start the same endeavor now in aging, and it will also last forever, and who knows when you... I argued, I think that's, he was absolutely wrong, and we actually dealing with a disease which is much easier. Why? Cancer is a moving target. It's a Darwin selection creature which changes all the time because of cell division. The cells actively avoid treatment by inventing new ways how to live. With aging, if indeed it is associated with senescence, senescent cells cannot divide. They cannot, through that, acquire new traits and amplify them. And moreover, you don't need to eliminate all of them to reach the point, meaning that cancer and aging seem to be, from the standpoint of treatment, are diseases of completely different degree of complexity, aging being 100 times easier. So, well, we started our program by trying to do the following. There were 4 principal ways what you can do. You can either block secretion by senescent cells, prevent accumulation, eradicate them, or reverse senescence. We didn't want to reverse senescence because we believe that that may actually create risk of cancer. We also found that there is an agent which naturally blocks secretion by senescent cells and prevent the accumulation. It's a natural antibiotic, rapamycin, and we're working with that. It's not the topic of today's talk, because today I want to just show you that we decided the biggest effort we put on the eradication of senescent cells, because that is the most cardinal way to clean the body periodically from time to time from these poisonous creatures who are, sitting with us, inducing multiple predispositions. And we did it in 3 different ways. One is most academic. We went to target identification in order to be enlightened with what is wrong with them, where is their Achilles heels, and follow that. We wanted to make vaccination to find antigens in them. And the third one, before we know the target and before we know antigens which they can be distinguished from other cells, we decided to take the old-fashioned approach which human civilizations took for thousands of years, empirical approach, but do it in a modern way. We presumed, we hypothesized that senescence is the druggable phenotype, that they do have targets even we don't know them, and therefore we decided to apply cell-based screening of hundreds of thousands of chemicals to see those who would be selectively kill only cells in senescent state. So the idea is that with time, there are senescent cells accumulated in the body which by their secretion create the microenvironment change, that by eradicating them you can significantly revert the situation. So, and what we want to isolate, so-called synalytic compounds. So there are plenty of questions. We do not know cells of which type in the body senesce, and which senescence is more important for the impact of that is more important for the disease, for aging itself. We do not know whether senescence caused by DNA damage or RAS oncogene are the same phenotypes. We do not know whether they have any additional function, what will be the consequences. So we decided ignore all these questions and simply go directly into the following thing, which we actually already have done. We took the library of about 500,000 compounds, and we made 7 readout cell systems, 7 different cell types of different species, mouse, rat, and human, turned into senescence by different means, including RAS oncogene, bleomycin, gamma radiation, and others. As a result of screening, we isolated primary hits, compounds which selectively showed a good degree of selectivity. Then they passed through validation, and then each result of each screening was overlapped, it's a Venn diagram, with others. And we were pleased to see that a good proportion of hits, and there are not that many hits, by the way, there are hits which are universal, meaning that senescence made in different species by different means in the end has similar target if you have the drug which can kill every senescent cell regardless how it was generated. So we took these compounds, they are prototype drugs, they are far from being perfect, far from being efficient, and they are currently going through the process of, well, first of all, they are tested on the extended panel of senescent cells. Then we are selecting or making those which can work pharmacologically in vivo, so we are putting them in mice in which senescent cells are labeled and look at those which will be able to reduce this luminescent. And then those who really work in that, we are testing in multiple models. One of which, of course, the most interesting thing is to put in an aging model, chronological aging, and see what will happen with these mice. And the second, we are using mice in which cancer is enhanced by presence of senescent cells, and they are very strong enhancers of engraftment or in metastases, and see it's a much, much faster assay, of course. Just to show you several illustrations. A, we can isolate compounds of this kind. Please look at this picture. So this is the same cell type, but in 4 different states. Senescent, when they were senescent by DNA damage treatment, and you see they acquire a certain marker of senescent, beta-gal staining. They can be differentiated into fat cells. They can be quiescent because of low serum or high density, or can be proliferating. And you see there is a compound, when you put it on these cells, the only state in which cells become vulnerable are senescent. So here you see the same compound is working. This is mouse, these are mouse cells, this is human dermal fibroblasts, this is mouse lung fibroblasts. And another thing, the similar compounds are working in epithelium of prostate. And I can tell that prostate cancer is believed, thanks to Pandolfi's series of work, originating in the organ which becomes chronically inflamed because of accumulation of senescent cells. This is in vitro mimicking of that. So this is normal human prostate epithelium growing young together with senescent cells. And you see that the same monolayer was treated with 2 different hits were isolated, and we see that the young cells are there, but there is a dramatic reduction of senescent ones. So we are approaching the idea of eradicating the background for prostate cancer, as it happened with H. pylori eradication, leading to eradication of gastric cancer. So now, whether it works in any of the events where senescence is accelerating cancer, the answer is yes. Remember, I showed you that the mice which were irradiated early in life, even very, very late in life, stay very prone to supporting metastatic growth of melanoma. If, however, you put into these mice melanoma cells, and after that you treat them with senescent compound, you dramatically reduce the number of metastases, indicating that you can revert this thing associated with accumulation of DNA damaged cells. And finally, the most maybe ultimate important thing is to check what it does to the aging organism in vivo. And I completely agree that we do not have a biomarker of aging. We are working on that, by the way, so that by the drop of blood you can say what is your physiological age. Today we are not there yet. That is why we are using very complex frailty index, which is being used in gerontological clinics. So it's cumulative measurement of we are measuring 26 physiological parameters of the body which are known to change with age, and the degree of separation and amplitude of separation of this parameter from its young state, which we are comparing with, is being recorded and put into this coefficient. So you see that both males and females with age, this is age in weeks, their frailty index is increasing. So what we did, we took mice, NIH Swiss mice, and when they already were kind of not really old, but in the middle of their life, when they were about 89 weeks old, we treated them for 1 week with 5 injections of one of the synalytic compounds which happened to work in vivo. And after that, we just maintained them, and the experiment is still ongoing. So this is a natural death curve of placebo-treated animals, vehicle-treated animals. These are animals which are which were treated with only 1 week with this compound, and most importantly, that 10 weeks after they were treated, and the 2 groups were their frailty index and these are different parameters of frailty index, were compared, there is a pretty dramatic reduction in the frailty index in the group which received this treatment, meaning that our hope received additional support, that maybe we're on the right way, and maybe aging, if at least to extent it is dealing with senescent cells, a potentially treatable disease. So without separation, without asking, asking for questions, I'm giving the podium to Katerina, because you noticed it's our joint talk. She will continue by showing you what we found on the way of doing this work, which actually, in my opinion, even more interesting than what I said. Please go ahead.